All right, welcome back to Engineering 117. A couple of quick announcements before we get started. Let's see, if you look at this guy, the exam schedule, okay, 9th of June is when the homeworks 1, 2, 3, and 4 are due. So this should be a pretty good review of what you should have picked up in Engineering 17 course. Then on the 10th, you see, on the 10th, that's the exam 1. That's the review exam for chapters 9 and 10. Okay, so that's something you want to pay attention to. What else? Okay, let's see, there is a link here that says formula sheet. Okay, so on Moodle again. So that you can use that for your homeworks, for your exams, for your quizzes, but just to let you know that such a resource is available. Okay, that's it. Any questions, comments, concerns? Okay, all right, let's do this. Let's quickly review what we did in the last class. Okay, what we did is to look at the sinusoidal steady state analysis. Okay, and I mentioned that sine and cosine can be interchangeably used, but just by changing the frequency or the phase rather, by changing the phase. Okay, and then I provided some information about how sine and cosine can be interchanged, what a root mean squared is. We went over some examples in terms of the sinusoidal analysis, okay, which is a steady state response that we were interested in. Okay, what else? Then I talked about the Phasor domain, right? Especially, I talked about the 3 domains: the time domain, the polar form, and the rectangular form. And the intuitive idea that um, I, I mentioned in the last class is they're all fundamentally the same phenomenon, but you want to be careful, judicious, and smart in picking which form to use where. Polar form when you're multiplying and dividing. Rectangular form when you're adding and subtracting. And in time domain, it's just to understand the frequency and other components. Okay. The frequency component is not obvious in the polar and rectangular form. Okay. And I showed you the unison, the unity between the 3 forms. Okay. You could have a person walk at 45 degrees, okay, northeast, and reach the same point as if they walked eastward and then head north. Okay, so one represents one form along the x-axis, and northward is the rectangular form, and then taking the oblique direction at a 45 degrees angle, that's a polar form. Okay, questions? What questions do you have so far? Okay, so there's a rectangular form, there's a polar form. You can go back and forth between all of those. Okay, and I showed you how to solve some problems, how to translate and then do some circuit analysis problems. Okay, of course, the RLC components in the frequency domain. Okay, and I must have given you the mnemonic, Eli the Iceman. Okay, voltage leads the current in an inductor, whereas the current leads the voltage in a capacitance. And then we understood the reason and the waveforms there. Okay, let's see. What else? Chapter 9 PPT. Okay, and then of course we did not go into the details of all of this. Okay, in the frequency domain, we did not do the source transformations, Thevenin's equivalent, Norton's equivalent. We did not do any of that, but I still provided YouTube links for you to go and explore. Okay, now from there, let's see If we can visit a new topic today, okay? Let's visit the topic. The textbook says the topic is 9.10, I think. Okay, 9.10. Let me add a page here. This is the cool thing about Notability app. I can annotate on my PowerPoints and add pages, okay, wherever I wish and like. Okay, so 9.7, it's called the, is it 9.7? Let me take a look. 9.10. 9.10. Okay, 9.10, a transformer. Okay, but like I mentioned, and it's always my practice to keep this as simple as we can, and more or less provide intuition, okay, rather than getting lost in calculation. Okay, so I'm going to call this demystifying the transformer. Okay, we may have or may not have seen this in the previous class, Engineering 17. Okay, but it's always a good practice to understand the first principles. Okay, the idea of transformer is basically coming from mutual inductance. Okay, when you bring two inductors close by, when you bring two inductors um, close to each other, this is 6.4, and then mutual inductance itself is an extension of the idea of inductance. Okay, an idea of inductance. Basically, you take a wire, wind it, that becomes an inductor. Okay, now if you pass a time varying current through an inductor, okay, this time varying inductor sets up a magnetic field. Okay, this is the first principles, understanding the physics underlying this. Okay, so there is an underlying, okay, there's an underlying um, magnetic field that is set up by this inductor. So this magnetic field is also time varying. Okay, so what happens is this magnetic field actually induces a voltage. Okay, so the voltage V of t is L di by dt. That's the idea of an inductor. Okay, you take a coil, take a long wire, okay, and turn it and make it into and wind it into a coil with a number of turns and pass a time varying current. What happens is there's a magnetic field that is physically set up. Okay, this magnetic field, what it does is to um, induce a voltage. Okay, now if you do it with a very similar inductor somewhere else, okay, there's another current I2. Okay, let's call all of these as I1 of t. Okay, um, and then there is an inductor L2, whereas this guy is L1. Okay, now this inductor sets up a which color shall we use? Okay, sets up a magnetic field of its own. Okay, a magnetic field of its own. Okay, This inductor sets up a magnetic field of its own. So this induces a voltage V2 of t, that is L di2 by dt. Okay. Now, the idea is simple. So these are called self-inductances. Okay, these are called self-inductance. The inductance or the voltage that is set up by the pink magnetic field. Okay, now this guy V2 is called, this is induced by self. Okay, self meaning L2 produces a green magnetic field, and that magnetic field creates a voltage in L2. Okay, but the idea is this is where it gets really interesting. If you were to bring these two closer to one another, okay, then what happens is this green magnetic field produces a current, or it produces a voltage in L1. Okay, let's see, let me do it this way. Okay, let's see, let's pick the same color here. Okay, because of the green magnetic field, there's a voltage that is set up in L1. And also because of the purple magnetic field, there's a voltage that is set up in L2. Okay, so these two inductors are so close that one begins to develop a voltage in the other. Okay, and that's the idea of mutual inductance. Okay, that's the idea of mutual inductance. Okay, when two inductors are so close that the magnetic field of one is affecting the other. Okay, so there are two kinds of voltages. One voltage coming from itself, the inductor itself, and the other voltage coming from the neighboring inductor. Okay, and then there are some M equals to K times square root of L1 times L2. There are some formulas, formulae, if you prefer that verbiage, okay, where the mutual inductance is some coupling factor K times square root of L1 um, multiplied by L2, so on and so forth. But that's the idea though. Remember, I wanted to give you the intuitive understanding. So when there are two magnetic inductors having their own magnetic field showing effect on each other rather than on their self, that's the idea of um, mutual inductance. Okay, questions please, questions so far? Everybody with me? Okay, let's do a simple problem here. Let's do a problem. It's not even a problem. We will develop this idea a little further. Okay, let's see if I can add a page somewhere in here. Okay, so again, I'm providing a summary view. I'm not spending a whole lot of time. So all of this is again, I'm not spending a whole lot of time getting lost in the nitty-gritty details. I'm just providing a summary view so you can understand and follow the lectures more comfortably from Moodle. Okay, all right. So let's see. Whenever you have a coil, a wire, okay, a long wire, it does not come free of charge. There is some resistance associated with it. So you want to make sure you take into account the resistance of that guy as well. Okay. So let's say I have a voltage source VG, and then this inductor with its long wire has a resistance of R1. Okay, so we are elaborating on the idea of mutual inductances, and then within its proximity there is another inductor L2, okay, which in itself has its own resistance R2 because it's a very long wire, metal wire, right? And then that guy is not driven. Okay, that guy is not driven by a voltage. Okay, so the idea is how can we apply KCL, KVL, and maybe Pratham, your question will become it'll become much more clearer. Okay, even though we did not answer your question about KCL, KVL, you will be able to see that in action now. Okay, let's see. Let's see what's going on. Okay. All right. So I'm going to demonstrate the idea of using the dot convention. Okay, meaning we have to have a way of determining the right polarity in which these voltages are induced. Okay, so in order to do that, we use what is known as this dot convention. And I'll talk about that in 1 second. Okay, when I'll talk about that in 1 second. Okay, so we are interested. Yeah, so let me completely draw this circuit. There is a current I1 flowing in here, and there is a current I2 flowing in this direction. Okay, there's a current I2 flowing in this direction, and then the amount of mutual inductance really is M. Okay, the amount of mutual inductance is M, and let's say that there is these dots. Pay attention to these dots; they're important. Okay, so what we are trying to do is to write KCL, use the dot convention, and of course, set up equations. Okay, set up equations um, using mesh um, mesh current method. Okay, so whenever you see problems, here is another tidbit of information. Whenever you see problems using inductors, not inductors, but transformers and mutual inductances, you want to use mesh current method. Okay, you want to use the mesh current method or write KVL in a bunch of different times. Okay, so the first thing I'm going to do is write KVL, Kirchhoff's voltage law, in the left loop, in the loop with the current I1. Okay, specifically, I'm talking about this loop. Okay, that's this guy. Okay, all I want to do is to follow one particular direction. Okay, and then add up all the voltage drops. Okay, add up all the voltage drops in the loop. Okay, so let's start with this guy. Let's start here. Okay, we start there and then follow the direction of the current. Okay, we start at the bottom left and follow the direction of the current. Let's bold in this. Okay, so I am going to annotate this as plus and minus, this is plus and minus. So here is how we write the KVL. We start at the bottom left corner, follow the direction of the current. I encounter a minus VG first. So I write a negative VG. Okay, then the next thing I encounter is R1. So the voltage drop across R1 is R1 times I1. Okay, then I encounter this inductor. Okay, so the voltage dropped in the inductor is L1 d I1 of t by dt. Okay, that's not it. Okay, that's not it because I still have to take into account the mutual inductance. Okay, so the mutual inductance is going to be M. That is coming from the mutual inductance. Remember, it's this magnetic field that's setting up a voltage here. Okay, that's the idea of mutual inductance, right? So the green magnetic field is setting up a voltage, inducing a voltage in L1. So in order to be accurate to my earlier diagram, I should really say there is a mutual inductance part that is coming from the green magnetic field. Okay, so M di2 by dt. Okay, so M di2 by dt is the voltage that is set up in the first loop because of the other inductor. Okay, but we still don't know whether it's going to be positive or negative, and this is where our dot convention comes in. Okay, the dot convention for setting up mutual inductances, the voltage of mutual inductances is this guy. Okay, um, look at where the dot is here, and where is the corresponding reference current entering. Okay, in the left loop at the dot, reference current is entering, okay, entering the inductor, and at the same time at the dot, which is down below, I2 is leaving the inductor. Okay, I2 is leaving the inductor. So that's the idea of, so using this, we can determine the sign for M2 or sign for this guy. Okay, we still don't know the sign for this guy, but the dot convention says when both of these are opposite, then select a sign of negative. Okay, so when one current is entering and the other current is leaving, then what you want to do is to select this guy to be negative and this guy to be positive. Okay, then you have your current opposite. Okay, that determines negative. All of that equals to 0. Okay, so let me go over this one more time, and I'm going to clear all of this in a minute, just now. Okay, okay. Now here is the idea. We are writing the KVL equation. So the first voltage that we encounter when we start going in this direction is VG, but because the negative terminal of VG is coming first, I incorporate a negative VG. Okay, then there is a voltage drop coming from this resistor. Okay, that's this product R times I. Okay, then there is a voltage that is set up by this inductor. Okay, that's set up by this inductor. That's LDI by dt. Okay, that's not it. Interestingly enough, this inductor as well sets up a voltage in the left hand loop because of the mutual inductance. And that's that component. Okay, and then how did I determine the directions for the polarity for this to be negative? Well, I used the dot convention. Okay, and I'll establish the dot convention a little bit more when we solve this KVL on the right hand side. Okay, but for now, this is the idea. Okay, so now you can simplify this. You can simplify this to negative VG, and then factor out I1, factor out di by dt, so on and so forth. But I'm going to leave it just there. Okay, just that I'm going to highlight this to be equation 1. Okay, so this is coming from KVL in the loop, left hand loop. Okay, Let's do the same thing. Let's see if we can apply the KVL in the right hand loop. We'll copy this, okay? And let me apply this, add a page one more time. Okay, paste it. So let's revisit this just like we did not, as if we did not encounter this at all. Okay, let's revisit the whole damn thing again. Okay, with fresh pair of eyes. Okay, so what I want to do is to set up KBL around the right hand loop, or the loop that has this guy. Okay, that has this guy. Okay, that loop is what I'm interested in. Okay, let's see how I can set that up. That's the right hand mesh. Okay, so let's start defining the currents. Let's follow this current direction. We'll call this plus, we'll call this minus, we'll call this direction plus and this guy minus. Okay, because we are following the current direction of counterclockwise in I2. Okay, so if we start here, it doesn't matter where we begin. Okay, we'll begin our analysis, I don't know, somewhere there arbitrarily. Okay, so L2 di2 by dt, so this is the voltage drop in this resistance. Okay, that's this guy. Follow the direction of the current, then you will see the resistance R2 times the current I2 times I2 of t is the voltage dropped in that resistance. But because the positive and negative are aligned with the direction of the current, you write a positive here. Okay. Then, so that's two components, two voltage dropped. Okay. But then let's not forget the third voltage drop. So the first voltage drop is coming from the self-inductance right there. Okay, the second voltage drop is coming from this R2 voltage dropped in the resistance. But then this guy, remember the magnetic field of this impedance through this mutual inductance actually induces some voltage drop in the other. Okay, so in order to account for that, okay, in order to account for that, I'm going to say mutual inductance times d by dt of I1. Okay, so that's this guy. Okay, both of these have the same form, LDI by dt or MDI by dt. Okay, because this is a self-inductance, I2 induces a voltage in itself, whereas this is the mutual inductance. So this guy is induced by the opposite current, I1. Okay, now the other part I have to remember is determine is whether I write a plus or a minus here. Okay, everybody with me? So there are three components of a voltage in this mesh. First component of the voltage is the self-inductance. Second component is the resistance. And the third component is the mutual inductance. So mutual inductance. This is the resistance voltage dropped. And this is the inductance voltage dropped. Self-inductance, to be more accurate. Okay, so we are at a point where we have to determine whether this is positive or negative. Okay, and for that, this is where we use the dot convention. Okay, let's see. We use the dot convention. Okay, let's see. Here is the deal. Let's pay careful attention. The reference current I2 is leaving the dot in the mesh, whereas I1 is entering. Okay, I1 is entering. So what we do is, so in order to determine the sign, I place a negative over here and a positive over there. That's the dot convention, right? So let me clarify the dot convention one more time. I2, okay, I2 at the dot, leaving, okay, and I1 at the dot, entering, okay. So if you look at the dot here, I1 seems to be entering the inductor, going, that's the direction, whereas I2 seems to be flowing in this direction, or it's leaving the inductor. So they're opposite. When they're opposite, okay, when they're opposite, then I'm interested in this node, right? At that node, I get a negative, okay, and this is a positive, which is along the direction, okay, which is I1 is entering and I2 is leaving with the dot, okay. So we end up with a, let's see, positive here. So if I2 is entering at the terminal, then positive at the other dot, okay. So that's the sign convention, dot convention, okay. I2 R2 plus L2 times di2 by dt, and then M di1 is a negative sign, okay. When the reference direction for a current leaves the dotted terminal of a coil, okay, the polarity of the voltage that it induces in the other coil is negative at the dotted terminal, okay. So here is the deal. Let's get rid of I2 for a second, okay. Okay. When the reference direction, when I1 is entering, okay, when the reference direction for the current enters the dotted terminal of the coil, the reference polarity voltage that it induces is positive, okay. If not, it is negative. So it's entering here. So this guy is positive. So there's a positive and negative terminal, okay. Let me be very clear one more time here. I'm just looking at I1, the direction of I1, right? I1 is entering the dot. So this becomes positive and this becomes negative. And because this is opposite to the direction of I2, I end up with a negative. Okay, let me go back and clarify what I'm doing here. Okay, let me go back and show you what I have done in the earlier problem as well. Okay, in the earlier problem, I wanted to find the direction of the voltage dropped or voltage setup as a result of I2. Okay, so because I2 is leaving, I2 is leaving the dot. Okay, you see, I2 is leaving the dot, leaving that node out of the inductor. So what happens is, as a result, the voltage that it sets up is negative at the dot of the other terminal. Okay, so therefore it's negative. Looking at the reference direction current, negative at the dot of I1. Okay, you get the idea. Okay, okay. There are a couple of things that we want to do here. The first thing we want to do is to notice the reference current. Okay, I1 is the current that is causing a voltage drop here. Okay, so I1 is causing a voltage drop and it is entering. I1 is entering. I1 is entering. Therefore, the L2 dot becomes positive at L2. Okay, that's not about the total voltage drop though. That's just about L2. L2 is positive, meaning the other voltage is negative. Okay, so positive at L2 because I1 is entering the dot. Okay, now this positive and negative has to be correlated along the direction of I2. So because I2 is counterclockwise, when you're writing the KVL, it sees a negative voltage. Okay, that's the reason why we end up with a negative voltage. Okay, now that said, all of this equates to zero. Okay, so that's the idea of KVL, right? The total voltage dropped. Okay, the total voltage dropped should sum to zero. So the voltage dropped because of the mutual inductance, and the voltage dropped because of the self-inductance, and the voltage dropped because of the um, resistance. Okay, because of the resistance. Okay, so there are three colors and three components here. The blue color is the self-inductance, voltage dropped, and uh, the pink color is the voltage dropped in the resistance, and the green color is coming from the mutual inductance. So these are the total voltages dropped in this loop, right? And then KVL says when you add them up all carefully with the proper sign, they should equate to zero. Okay? Questions, please. Questions so far. Is everybody with me? How many people did I lose in terms of the dot convention and following the sign? How many of you think you could use an example problem on that? Okay, so you guys are doing good, which is great. Now, what we are going to do is to apply these top ideas. Okay, apply these ideas. So all we want to do here is simply let me go back to the idea of intuition. Okay, don't get lost in these calculations, these messy looking equations. All we want to remember is that when you're writing a mesh equation, KVL, in a loop that has a mutual inductance, you have to account for the self-inductance, the resistance, and also the mutual inductance component that is coming from I1. Okay. Similarly, when you're looking at the loop on the left-hand side, where I1 is the main current, there is a voltage drop. Okay, there's a voltage drop, green color voltage drop. Okay, here from the in the direction of the loop. Then there is this guy. Then the voltage dropped in the resistance. Okay, then there is the voltage dropped in the self-inductance. And then, of course, the only thing that we want to remember is that this blue inductance is coming from I2. You see, there's an I2 component in here. Okay, there's an I2 component in here. Okay, that's the mutual inductance coming from the other loop. Okay, that's the intuition that we want to remember. Questions, please. Questions so far. Now, if you guys are not comfortable asking questions over the microphone, you are welcome to type them in the chat. And if you're not even comfortable um, chatting or writing a text, you are welcome to send a private message over Zoom to me. Okay, keep an eye on that. I try to keep an eye on that, and I'll be sure to not, speak your name out if that is how you prefer to ask your question. Okay, so this is the fundamentals of an inductor. Okay, of a transformer. There are two coils. There are two inductors that are so close that one has the other. The one has an effect over the other. Okay, so let's go to number 10 here. So let's quickly finish up this idea of mutual inductance, because that is important for our transformer. Okay, so um, these are all the ideas that I highlighted. The purple one is coming from a voltage drop in VG, or voltage supplied by that guy. Then the voltage dropped in the resistance, then the self-inductance, and then there's the mutual inductance. Okay. Similarly, when you write KVL on the other hand side, right hand side, there is the voltage dropped in the resistance. There's voltage dropped in the self-inductance. Okay. And of course, there's the mutual inductance. Okay. So you want to account for that. Okay.
Professor,
Yes.
why can you go back up? There's a on the right side. There's a voltage drop across the resistor.
Here.
Yeah.
Okay. Yes.
Um. Okay. Just looking at the equation, it says it's negative. Below that one, it says negative. Yeah, that one. It's a voltage drop, correct?
It's a voltage drop, but you want to make sure you're doing it um, in relationship to I2.
Right.
Okay. So, or the way the textbook set up this equation is different. Okay. It followed, let's do the KVL here, starting at this node. Okay. Let's start at this node. Okay. It comes down to the reference direction that I choose. If I'm going in the clockwise direction, okay, I
Oh.
see a negative positive direction for LDI by D2,
Yep.
and then a negative positive direction for resistance. That's why it's negative. And then the opposite for you see what I'm saying?
Yeah, yeah. I just saw that the current was going opposite to that, and it looked like it was flipped. But you're oh, I see what happened. Okay.
Okay. So they're essentially the same. We started with this. We followed the direction of the current, and you're referring to this one. But then, you know, the textbook chose to do it a different direction.
Gotcha. Okay.
Th-
Thanks.
Thank you. That's a good question. It's a good observation. Okay. So that's the idea of writing KCL and KVL. KVL. Okay. And then don't get too lost in these equations and all of these nitty-gritty details. Just pick up what you need. Okay. And what is essential to preserve intuition is what you will hold on to. Okay. Let's see the transformer. There are two kinds of transformers that we will be looking at. Okay. Page number 350, I think. Okay. Page number 910 is a linear transformer. 911 is ideal transformer. Okay. So in here we use this M equals to K times root L1, L2. Okay. In the ideal transformer, we make some assumptions. We make K equals to 1. Okay. And we call L1 equals to infinity, L2 equals to infinity. Okay. And R1 equals to 0 and R2 equals to 0, so on and so forth. So the idea is we can make some simplifying assumptions from the linear transformer and then make some insightful comments in ideal transformer. We'll talk about that later on. But what is a transformer? Transformer is simply that a device that's based on magnetic coupling. Okay, if you have seen this mutual inductance, that's exactly what is at play in an inductor. Okay, in a transformer. Okay, that's what is at play in a transformer. In communications, transformers can be used to match impedance and between two circuits to eliminate DC signals. It can be, you have seen many of such transformers. They're used for stepping up, stepping down, um, converting voltages from different levels to different levels, so on and so forth. Okay, it's very common. Here is the typical transformer. Okay, like I mentioned, let me demystify this a little bit. Okay, there is a coil, there's an inductor that we are familiar with that is magnetically coupled to the other inductor, right? Through the mutual inductance topic that we just discussed. Okay, and this resistance is coming from the long wire. Okay, this resistance is coming from the long wire that makes up the turns of this inductor. This guy, let me color code this differently. Okay, this guy also is an inductor, and then that because that's a long wire that has a resistance of its own. Okay, then let's say I'm trying to apply an input signal. Okay, now an input signal source is not ideal, but it has a resistance of its, an impedance of its own. Okay, it has an impedance of its own. So ideal voltage source is not possible. It has some resistance. So that's what we have as ZS here. Okay, then the only circuit element that is remaining here that we did not yet visit is this guy. Okay, let's see, which is the load. Okay, this is the load that we are trying to deliver the power or voltage or current to. Okay, so this is the external circuit which we are trying to drive. Okay, those are the different components. Let me say that again. There is this purple inductor, and because inductor is a long wire, it has an associated resistance R1. Okay, then J omega L2, that guy is an inductor in itself, and it has an associated resistance R2. Okay, then there is a voltage source shown in red, Vs, and then there is an impedance associated with the voltage source. Okay, let's see. So R1 is the resistance in the primary. Primary is where you apply the voltage source. Okay, and then there is a mutual inductance M, and written in the frequency domain, we have J omega M. Okay, similarly, R2 and L2. Now, what I'm going to do is to represent everything in the frequency domain. Okay, instead of using L1 and L2, and instead of using L1 di by dt, I simply use J omega L times I1. Okay, in the time domain, I have to write the derivatives, whereas in the frequency domain, I simply can use Z times I form. That's what we discussed in the last class, right? So all I'm doing is the exact same idea that we discussed so far, except that we are doing all of that KCL in the frequency domain. Okay, let's see. So if I were to write the K, and I'll come to the reason as to why I am writing the KCL and KVL uh, in a minute. Okay, but let's try to look at this loop. Okay, the first loop, the left hand side loop, and write KVL in this loop. Okay, if you look at KVL, if you try to write KVL, there is 1, 2, 3, 4 components that are dropping the voltage and a mutual inductance coming from this source. Okay, current I2 is also going to drop a voltage in this loop. Okay, that's what we discussed in a mutual inductance idea, right? Um, so that's exactly what we are doing here. Pay attention. There is this purple. I'm going to clarify this, clear this up. Okay, when you write the KVL on the primary side or the left hand side, when you write the KVL on the left hand side, you start here and go around the loop. It's exactly what you will find. There's a negative Vs over here. And sure enough, you find that negative Vs. Then, okay, then you see this negative Vs. Then there's a Zs that is dropping voltage in the same direction as I1. So there is a Zs times I1 voltage drop in this guy is over here. Similarly, there is a I1 R1 plus minus the direction of current is also I1. So the voltage drop in this guy is over here. Okay. And then there is the self-inductance of J omega L. Okay. Self-inductance of J omega L. J omega L positive and negative direction. J omega L1 times I1. That's this guy. Okay. So those are the three components. And if you account for this guy as well, you account for this guy as well. That's 4 components that you can readily see. But let's not forget the 5th component, which is the mutual inductance. Okay, that's most important component when we are looking at the inductors, when we are looking at the transformers. Okay, let's see. How do you calculate the mutual inductance? Okay, so we are interested in finding out the voltage drop that this current I2 from here causes in this loop. Okay, so we know M is the inductance, so J omega M times I2 is the voltage that is J omega times I2 is the voltage that is dropped. And in terms of deciding whether this is positive or negative, what we have to do is to understand, okay? What we want to do is to understand the dot convention, okay? So let's pay careful attention. Now the idea is I2 is leaving the dot, therefore the resultant voltage drop is going to have a negative at the dot and positive the opposite. Okay, so I2 induces a polarity that is similar to this. And now we want to take into account how I1 is going. I1 is going in the opposite direction, hence we end up with a negative. Okay, sure enough, we end up with a negative sign here because the voltage induced is opposite to the direction of I1. Okay, so that's KVL, Kirchhoff's voltage law on the left-hand loop. You can do the exact same thing on the right-hand loop as well. Okay, if you think about it, on the right-hand side of the loop, let's do this fun thing. Okay, on the right-hand side of the loop, um, if you follow the direction of the current, okay, there is a voltage dropped here, there's a voltage dropped there, there's a voltage dropped there, and of course the mutual inductance term. Okay, so there are four terms that you would expect in the KVL of the right hand side, and sure enough there is 1, 2, 3, and 4 terms in there. Okay, what else? Let's try to follow this direction of the current. Okay, so I2 R2 is easy to find out. ZL I2 is easy to see, and then um, there's a J omega L2 times I2. That's a term that's dropped here as well. Okay, that's a current that's dropped here as well. Okay, so you want this to be positive and negative. Okay, you want this to be positive and negative. Okay, um, so uh, following the direction of the current I2 J omega L2, I2 R2, and I2 ZL are all in the direction of the current. Then there is a term, okay? Then there is the fourth term, the mutual inductance term, J omega M, that is set up in the loop for I2 as a result of I1, okay? Now what we want to do is to um, find out the polarity of this guy, okay? The polarity of this guy is determined by the dot convention. The reference current is entering the dot, therefore it leaves a plus on the other dot, okay? Plus on the other dot, and then this voltage dropped, okay, is in the opposite direction of I2, therefore you leave a negative over there. Okay, that's what determines this negative J omega M I1. Okay, you get the idea of all the different components involved when you're writing the KVL for a transformer, including the dot convention. Okay, questions, please. Questions so far. Okay, the rest is simply finding the right equations to substitute in. Okay, so for example, it's just algebraic manipulation at this point. Okay, the only thing that you want to remember is when you're setting up the KVL equations, don't forget the mutual inductance term. Okay, don't forget the mutual inductance term, and it has an associated polarity as well. It has an associated polarity as well. Now you can massage the equations to show that um, there is a Z11 term. Okay, we don't have to worry too much about it. There's a Z22 term, purely intrinsically all the impedances on the right hand side, all the impedances on the left hand side. Okay, what's on the left hand side? If you were to ignore, the mutual inductance, there are a bunch of different impedances. There is ZS, there is R1, and there is impedance from this guy. So just the um, impedances in the left-hand loop, that's what you call a Z11, ZS, R1, JL1, okay? Not taking into account the mutual inductance, okay? So Z22 includes R2, ZL, and J omega L2. Okay, that's all there is to it. It's simply understanding divide and conquer. Okay, so sure enough, Z2 includes the impedance in the left hand inductor, the resistance in the, I meant the right hand, okay, and then Z load, the impedance in the left hand inductor, the resistance, and Z load. Those three contribute Z22, okay. Similarly, ZS, R1, and this guy contribute Z11, okay. So manipulating algebraically is all there is to it, okay. And I'm going to point to you a few important results, okay. Let me see this guy, okay. I2 is J omega M times I1 over J22, whereas I1, okay, is this term. You can express I1 in terms of Vs, Z11, omega, M, and Z22. I1 can be expressed as a function of these parameters. Okay. Similarly, I2 can be expressed as a function of J, omega, M, I1, Z22. Okay. You can refer to the notebook notes that you have for calculating the exact formula, for remembering the exact formula. Okay. So that's the idea. So I1 is expressed in terms of the different parameters. Okay. I2 is expressed in terms of the different parameters. Okay. Important result. Important result. Because the problem asks you to calculate some results and nothing else. Okay. What else? If you want to look at the terminal behavior, or in other words, if you're looking into, let's see, let me highlight something here. Okay, let's see. Let's take a quick 2-minute pause here and review what we did so far. Okay, so far all we have done is to look at a transformer that looks like this, okay, in its frequency domain. And I wrote KVL on the left-hand loop, and we also wrote KVL in the right-hand loop, right? So KVL in the left-hand loop included this guy, this guy, this guy, this guy, 1, 2, 3, 4, and that invisible hand from the other side. Okay, so 5 terms in the left-hand loop. Then in the right-hand side, there is 1, 2, 3, and the invisible hand from the other side, the mutual inductance. So 4 terms. So I had 2 equations, 2 unknowns. I1 is an unknown, I2 is an unknown. So in order to find I1 and I2, we needed 2 equations. So the first equation came from the KVL on the left-hand side, okay? And then there is the KVL on the right-hand side, also called the secondary side, two equations, two unknowns. We should be able to solve for I1 and I2. These are the unknowns, okay? So that's what we have done so far. We looked at setting up KVL in two different contexts, okay? And then solving those two. Everybody with me? Okay, okay. Let's see if we can move forward, okay? So here is our transformer, right? The one that is highlighted here is the transformer, okay? There is the winding on the primary or the left-hand side, J omega L1. And there is a winding on the right-hand side, J omega L2, okay? And then there is the long wire that is wound into a coil, has some resistance because it's a long wire, okay, R1. And then there is R2 resistance coming from the long wire on the right-hand side. And then this simply means that both these coils interact with each other. Okay, that's what the J omega M simply means. Okay, at the core, that's a transformer. Okay, now you may ask, what's the other add-ons here? Well, the transformer has to be supplied with some input voltage. That's the input voltage. Okay, input voltage, and the input voltage source has some associated resistance. Okay, then what's the other thing on the right extreme? Okay, that's the output load. Okay, so here is my transformer. There is the input, there's the load. Okay, then we are going to slice it in every which way. Okay, once we slice it into input and output terminals, so this is the input side, right? If I were to look into this transformer, okay, if I were to stand outside of that purple box to the left of that purple box and try to look into those two terminals, what would be the impedance that I find there? That's the question. Okay, that's an interesting question because you want to match impedances. You want to make sure that the you carefully there are things that you can do by carefully matching the impedance, looking into the transformer. Okay, so the question we are interested in is, if we were to stand just outside that purple box to the left, right in between ZS and that purple box, okay, where that ZS ends, and in between those two places, and look into the transformer, how much impedance would I find? Okay, well, there's a mathematical formulation for that. ZAB is Z11 minus ZS plus omega squared M squared by Z22. Okay, let's not get uh, crazy about these calculations. I will simply show you the result that we are interested in, okay, or the intuition that we are interested in. Okay, let's see. Let's pay attention to the result here. Okay, ZAB equals to R1 plus J omega L1 plus some crap. Okay, that's this crap. Let me color code it carefully. That guy shows up here. Okay, let's try to understand the intuition here. Okay, we are interested in looking in to this transformer and finding out the total impedance. How much is the impedance looking in? Okay, and the result tells us when you do the math that ZAB equals to a component of this resistance, okay, and a component of this impedance, and some component from the invisible hand, okay, some component from the invisible hand, okay, coming through M. You see, M is the invisible hand, right, coming from the other side. Remember? So that's exactly what we have here. R1. Let me use the same colors as I used before. Okay. R1 is the resistance. Okay. Then there is the blue J omega L. Okay. Then there is this invisible helping from the other side. Okay. That comes because of mutual inductance. That comes because these inductances are so close that the magnetic field of the one affects the other. Okay. So ZAB has a component of R1. ZAB has a component. So looking into the ZAB has a component of J omega L1 plus some component of this resistance shows up on the left hand side. Okay. Some component omega squared M squared by R2 plus J omega 2 L2 plus ZL. Okay. Think about it. Okay. And this is a complex number. Okay. 1 over a complex number is also a complex number. Okay. For example, let's see, 3 over 3 plus 4j, 1 over 3 plus 4j. They're complex numbers. One is the inverse of the other. What do you think happens when you multiply the two? Well, it completely eliminates the complex part of it, and it just leaves the real number part. You don't trust me? Multiply this 3, 4j, and 1 by 3 plus 4j. Okay? Do the math either in polar form or in rectangular form. You'll find that the answer is, interestingly, 25. Okay? But where am I going with that? The idea is this. There is a reflection of Z22. What is Z22? Remember Z22? Let's go back to Z22. Z22 is the impedance. Let's see, where can I find this? Okay, Z22 is the impedance in the right hand side, J omega L2 plus RC plus ZL. That's the impedance on the right hand side, Z22. Okay, I'll show you. I'll show you what I mean exactly. Okay, go back. And then I mentioned that Z22 is ZL2 plus R2 plus ZL. That's the sum of all the impedances in the right hand side. Z22 is ZL2, R2, ZL, the sum of all the impedances in the right hand side. Okay, so here is the intuition part. Okay, when you're looking into the transformer, that is equals to the sum of impedances in the primary side plus some component of the secondary side. You see, That's the idea. It's called a reflected impedance. Okay, it's called a reflected impedance. Okay, and you'll find that you can express this guy ZAB equals to R1 plus J omega L1 plus omega squared M squared by Z22 modulus whole square into Z22 complex conjugate. Okay, I think it should be mentioned somewhere in here. There it is. Okay, and how is that the case? You simply have to look at the involved math. Okay, math involved. But for now, don't, without getting, I leave that as an exercise for you to go through the math involved. Okay, but what I will tell you is, again, if you look at the input side of the transformer, there is the input side impedance plus a reflection from the output side impedance. Okay, this term is called the Z reflected. Okay, this term is called the Z reflected. Omega squared M squared by solve this complex number, you'll get this form: omega squared M squared by Z22 whole square times Z22 complex conjugate. Okay, everybody with me? Questions so far? Okay, I do have a question for you. If you would you like for me to spend a little bit more time on this concept, or would you like for me to move on to the next topic? Any suggestions? I'll say Elijah, Martin, Natalia, Guadalupe. I'll say it says he's okay so far. Okay, okay. More comments in the private chat line. Okay, all right. So good. So all we are doing is looking at the reflected impedance. Okay, there are three components, like I mentioned. If you're looking into the input side of a transformer, okay, there are three components. Looking at the input side of the transformer, there are three components: R1, R2, and the reflection from the other side. Okay, that's all there is to it. Z reflection. Okay, now Z reflection has a formula. Reflected impedance is omega squared M squared by Z22 squared times the complex conjugate of Z22, where Z22 is simply the sum of all the impedances in the right hand side. Okay, just remember the important results. Okay, and then there's some example problem. We can look at an example problem, or maybe we can skip the videos posted by Professor Tetro. Do talk about these. Okay, so M is K times L1 L2 under root. Okay, so we should be able to find K if one of these is given, if three of these are given. If not, we can find the unknown from the known values. Okay, then find the reflected impedance is the question. So we should be able to apply that formula. Okay, first find Z22. and then omega m squared by Z22 will give us the Z reflected. Okay. All right. So when it comes to finding I1, it's simply applying this equation here. If you remember, I mentioned that there are certain important results that you want to remember. Okay. I2 and I1. Okay. I2 as a I1 as a function of Z22, Z11, omega m, and Vs. That's exactly what we use in the formula here. Okay, I2 as a function of omega m, Z22, Z11, and Vs. Okay, we find an expression for I1. Okay, should be able to write it in terms of the time domain form. Okay, once we have I1, we should, that's its time domain form. We should be able to calculate I2. Okay, we calculate I2 in its time domain form. Okay, then finding ZAB is again, if you remember, R1 j omega L1 plus Z reflected, just like that. R1 j omega L1 plus the reflection from the other side. Okay, I we do not have time to go over this example problem more um, elaborately, but all we have been doing is to apply the idea of mutual inductance. Okay, mutual. Okay, we apply the idea of mutual inductance. Okay, questions, please. Questions so far. Okay, so we have a few minutes, 5 minutes, but I don't want to use up the last 5 minutes to stuff more and more new concepts. I think we'll stop here instead of going into the idea of ideal transformer today. Um, but I do want to mention this. Okay, what you see in this class is not supposed to be a formal introduction in today's lecture. Okay, the formal introduction and the formal um, lecture on this is posted on Moodle. I'm just trying to demystify and give you more insights at a very big picture level instead of going into the nitty